Hello, everybody. So welcome to our first seminar of the year. Today we have a speaker, Maxim Bichuch, who is joining us from State University of New York at Buffalo. Maxim holds a Master of Science from NYU and a PhD from Carnegie Mellon, both in financial mathematics. He has been a postdoctoral researcher associate and a lecturer in the Orphy department in Princeton, and an assistant professor at WPI and Johns Hopkins University before joining the Department of Mathematics at University of Buffalo. Prior to obtaining his PhD, he has also gained corporate experience working for Citigroup and Bear Stearns. His research interests include optimal portfolio selection, optimal investment and consumption, optimal control with transaction cost, viscosity solution, stochastic volatility, credit, funding and counterparty risk, and most recently, electricity markets, machine learning, decentralized finance, and fintech. Today, he'll be talking about deep learning schemes. Thank you for accepting our invitation, and the floor is yours.
Thank you, Reem. Thank you, all the organizers. I'm very glad that you're continuing with this tradition and still doing the online seminars. Very good to be here. So yes, I want to talk about deep learning scheme for solving fully nonlinear partial differential equations. And this is a joint work with my former student, Kat Chen, who is now in industry. So I think the motivation is fairly standard, that be able to solve PDEs numerically is vital, especially in high dimensions, because typically outside of a few cases, there are no closed form solutions, and therefore we usually resort to numerical analysis. But in addition to high dimension, there is another difficulty that pops up when we try to solve things, and that is smoothness. So unfortunately, very often there are no classical smoothness of the solution, and only some kind of some weak solutions or some form of weak solutions exist. And so that creates a big difficulty, because when the solution is not regular, somehow you can just it's difficult to find it. And in addition, it's very, very difficult to prove its convergence. And on the other hand, classical numerical analysis, such as maybe finite differences or finite elements, suffer from course of dimensions, although in those cases there are proofs, there are classical proofs for convergence. Now, finally, kind of the third pillar is the Monte Carlo techniques, which do circumvent some of these issues, but again, convergence is typically slow and not very well understood. And so the goal of this talk, of this project, was to find a viscosity solution of a PDE numerically, but maybe perhaps more importantly, to show its convergence. So let me give a very, very brief literature review. So one bit is a little bit on deep learning, which I was surprised to learn that this is actually more than 30 years old area, starting from at least as far as I know, or as back as I know, from Lee and Kang from in the 1990. So there are a lot of work has been done recently. Maybe one of them just is Wen and al. That introduced a new algorithm to solve BSD numerically. And then a related follow-up work to that was the proof that it works. On the PD side, there was the paper by Seniorana Spiliopoulos, who present again a very nice deep Galerkin method with the proof of convergence. And this is perhaps a very related work, but one of the key assumptions there is smoothness, and in fact, very high degree of smoothness is required for the proof, for the convergence proof to work. On the other hand, maybe the key example in this talk is going to be the transaction cost problem, the example of solving it numerically. And so yet again, there's been a lot of work done. So these are just a handful of citations. Jinut and June discretize and solve the finite horizon optimal investment problem. Mutharaman and Kumar have a very, very nice numerical scheme for optimal investment and consumption in case of two stocks. And they have, I think, the first one to obtain these results numerically, but the proof of convergence was really presented only in case of one stock. And so related paper where Mutharaman described they have an iteration scheme for the free boundary problem, and again, proof of convergence was with a single stock. Gonin and all have a nice simulation-based deep learning approach to solve a related problem of risk-sharing equilibria. And then the actual transaction cost problem was again solved numerically by quite a few people. These are just two that solve, again, multidimensional problem, but again, without really having a proper proof of convergence. So let me start by introducing the problem setup and actually maybe spill the beans and tell you the main idea of our plan to tackle this issue. So here's the problem that we want to solve, and we'll formulate it more generally. So at the end, we want to solve the following PDE. Basically, heat equation. F will be quite general. We'll have a terminal condition. We'll assume that the domain omega is smooth and bounded, and capital T will be the terminal time. So we'll assume that F is elliptic and proper. In other means, basically well behaving in its arguments, monotone, specifically in the first and last argument. And we'll assume that ultimately the solution is a unique viscosity solution of the PDE. So we'll assume that we know that the PDE has a unique viscosity solution. And the key is that it need not be smooth. Now, if the dimension is low, then classically we can use finite differences, finite elements, and that will work well to solve this problem numerically. If the solution was smooth, right, in addition to viscosity, we would know somehow that it's quite smooth, then we can use the Soriano and Spiliopoulos method to show convergence of the deep Galerkin method. But so now the key idea is somehow to try and combine these two approaches and somehow show convergence, but without requiring key smoothness, but really only in viscosity case. All right. So here's the setup in more detail. So let's have N. This is going to be basically the mesh points of the domain. So I have my domain 0t cross omega, and I'll discretize it using some mesh points, delta t, delta x grid. We'll assume that it's basically all equal. And now let me have the finite difference scheme operator, this F delta t delta x. I'm going to abuse notation. Previously, UT was outside. I will, just for convenience, not to have it dangling, I'll put the time derivative inside this operator as well. So the F is basically, again, the discretized time derivative, plus the numerically discretized function f that I had before, right? So it has the first and second order derivatives of u. right? Or alternatively, maybe a little bit more conveniently, let me write f, this finite difference operator, as just a function of h, right? So it's going to be a function of delta t, delta x, right? Then, and the points t and x that I want to evaluate everything at, right? Then it's going to be a function of the function u itself, and then of the finite difference between u and somehow the adjusted points around the point t and x, right? Whatever that small neighborhood of points need be, right? For my grid, for my mesh n. And so the key is to try and solve somehow now this finite difference scheme. In other words, I want to solve f delta t delta x, right, of this discretized version of u, right, that now lives on the grid, so u delta t delta x, right? So I want to solve it equal to 0 at hopefully all the points on the grid. Right, that's basically the classical finite difference scheme. Right, so now let me briefly recall somehow the key assumptions that we need in order to have convergence. Right, I should say that maybe somehow the key question, the first key question that has been known classically, is whether this finite difference solution on a grid, right? Let me just call it bracket u, right, is close enough to the true viscosity solution u, right? And that's a key result by Barnes and Tsouganides ultimately. And so the answer is yes, if you have some nice properties on your operator, right? So what do we need? We need, or some of the properties, ultimately I'll need some, we need others, but at least some logical properties to require from their operator are the following. So one is that we want the operator to be degenerate elliptic scheme. So ultimately, okay, so what do I mean by it? I want that my scheme is degenerate elliptic if it is basically increasing in the last two variables in each of the variables, right? So that makes sense because ultimately I've assumed already something very, very similar on the original PDE operator. So it makes sense that I will still require something like that if I have any hope that the solution to the finite scheme would be close enough to the true viscosity solution. Another thing is proper. So again, that's for the original operator. That's very classical assumption. For the difference scheme, it's basically almost the same thing. So f is going to be proper if it behaves somehow nicely in the this is the place for the actual function u. Right, so if the difference between different values of the function, right, if you take the operators, is going to be at least delta times the difference. Right, so again, if you think about the classical viscosity solution, that's a very, very nice and required property typically for viscosity solutions to work. Another thing, again, for the difference scheme is Lipschitz continuity. Again, something that makes sense. So this is just kind of stating the classical thing. Again, I'll want or we'll want the Lipschitz to be in anything that involves the function u. So u and its derivatives together. One more or a couple more definitions. So this definition is for a scheme to be consistent. Right, and ultimately, so what I want is that if I take a smooth enough function v c12, then evaluate the scheme on v, right? Then I want that the difference between the finite difference scheme and somehow my original operator, right, will converge to 0. as delta x and I forgot to say delta t, also delta t also converge to 0. Right? Again, that's something that makes sense. If for whatever reason you'll try to approximate a different operator, there's somehow little hope that the solutions will converge. So this is just basically kind of very much makes sense. One more is stability. And this actually, so the property is that if you fix the terminal condition and your scheme, then there exists a constant CT and J that again that may depend on the terminal condition, such that the norm, and I didn't really specify what norm, so typically it's L2, but basically a norm of your choice of the solution on somehow the x for the x points, right, can be bounded using the initial norms of the function u, and right, this should be here, right, for some for basically the terminal conditions for the using the terminal layers that we have. The intuitive meaning of this condition is basically that if, which numerically you'll inevitably will do, is if you have a small error in the terminal conditions, then this error would not blow up as you continue solving your function, and hopefully you'll have a good control on the error, so it should decay. If this condition is violated, then the scheme will be unstable. So this small perturbation, small error in the terminal condition will cause basically a blow up sometime later in this function if this condition basically does not hold. That's the intuitive meaning. And so the classical result of Barnes and Tsouganides was that if the scheme is consistent, stable, and monotone, then we have convergence. So specifically, we have the solution to the numerical scheme will converge locally uniformly to the true viscosity solution. The problem is that these conditions are quite difficult to work with. And so there is an adaptation by Obermann, who I'm going to be citing a lot, using kind of the other, some of the other properties that if f is consistent, sorry, just one A, consistent and degenerate, then basically this is enough. Then we will still have convergence. Well, so with this introduction, the next question is, how does this all help us, right? This is so far basically just classical, more or less classical numerical analysis. How can we use this? How can we adapt this to our problem? And so our main idea was, instead of just trying to directly try and solve deep learn the viscosity solution U, we will try to use the neural nets to approximate the finite difference solution, and then hopefully to show convergence to the discretization U delta T delta X. Due to the existing results, we already have that that the finite difference will converge to the viscosity solution. So as long as we can show convergence to U delta T delta X, we should be golden. And so that's ultimately the goal. And so now that it's clear, I think the rest is basically just a little bit or some technicalities. Right. So number one, probably the most important thing to do for neural networks is to specify the loss function. I think in this case the loss function is fairly intuitive. If we want to approximate the numerical solution, they will take the loss function being basically the numerical operators, right? The sum of the numerical operators squared, and hope that we minimize it, basically hope that that it approaches 0, right? And then basically hope that everything works, right? So the rest, I think, is just technique, right? So number one, the space of the actually I thought I fixed it. Sorry, the shallow network with n neurons and just one hidden layer, and h being the activation function. Right, so Gn of h is just defined very classically, right? So this is just the linear combination of the activation functions, right? Theta, that's going to be the parameter space that will train the deep learning scheme, right? And if we take G to be the union of the Gn's, then, first of all, the solution to the finite difference scheme on the grid, if it's going to be in that space, will be the global minimizer, right? Because, of course, the solution is just identically 0 if it exists. And so, of course, will be the global minimizer of the loss function that we've defined. And so the first result is, again, due to Obermann. So number one, we're basically not trying to prove an empty set theorem. And again, so under our assumptions on the finite difference scheme, there exists and unique a numerical solution, a numerical finite difference solution, U delta T delta X. So that's good. It exists. And then second, so that's basically just a very simple corollary, not even a theorem of the universal approximation, that under our assumption, right, then for every epsilon there exists a function v, assuming the activation function is not constant, such that the loss is less than epsilon. So that's basically what we need, that there will be a v in our space that will give us a small loss. Now, another issue is that ultimately the loss function is some kind of L2 norm. Ideally, when we want, at least classically, when we want viscosity solution, we want some kind of local but pointwise convergence. And so, fortunately, that's also not very difficult to prove because again of the properties of what we're doing, because everything is basically viscosity solutions. And so again, under our assumption on the finite difference scheme, we can convert the L2 loss with some penalty to pointwise loss, and basically be given U delta T delta X, our finite difference solution to the finite difference scheme. Right, again, given our epsilon and assuming that the neural network, the loss is less than epsilon, then the pointwise loss is going to be fairly small, order of square root of epsilon, right? If you compare it to the difference between the neural network and the finite difference solution U. So that's basically kind of the key results that we need, right? Because at this point we have we've completed this triangle, right? So the neural network is going to be close to the finite difference solution. In turn, we know that the finite difference solution will be close to the true viscosity solution. Right, and so now again there are some technicalities, but basically the key idea is clear. We should, as long as everything and all the assumptions can be satisfied that we have imposed, we will have the desired convergence that we want.
Can I ask a question, Maxim?
Yeah, of course.
I will allow myself to interrupt. So in the previous slide, right, C is what does C depend on?
Good question. I think it depends, if I remember right, it basically depends on everything, right? So, I mean, of course, not epsilon, but basically everything else. All the parameters, the grid, the grid is fixed here, right? And everything.
But if if the grid becomes larger, C is becoming larger too?
I want to say yes. I have to double check, but I think, yeah, ultimately, yes. Yeah. So you have to somehow fix the grid for epsilon, right? And then once you do that, then you have you need to find the neural network.
I see. Can you, if you had additional smoothness on the solution itself, can you make it grid independent?
So I think then you have, if you have smoothness, then I think this is basically a real overshoot. You can have basically just the classical methods, and convergence would work just fine. It's really I mean, specifically, right? I mean, we expect that in the transaction costs, right? You have smoothness inside, but it's the apparent lack of smoothness on the boundary that basically makes everything really bad.
Okay, so okay, thank you.
Yep, thanks. Yeah, so it's really the lack of smoothness that makes all of this relevant and needed. So as I was saying, now let's try to apply it to the optimal investment problem in 2 dimensions, as even that is quite non-trivial. And as always, the key interest is going to be that the stocks are going to be correlated, and I'll kind of show you why this requirement makes so much trouble and creates so much problems. So as I was saying, number one is that there is a strong suspicion that the value function is not smooth, although I'm not aware of a proof. But I think in case that's the truth, the stocks are correlated. I believe that's true. Right. So the setup is going to be that let's have a standard n-dimensional Brownian motion on a filtered probability space. We'll have correlation. Ultimately, we'll reduce it just to 2 stocks, but we can formulate it for n. Positive, no, negative. R is going to be the risk-free rate, and mu I, sigma I are going to be the expected return in the standard deviation of the stock. So let me denote by X and YI to be the amount of wealths invested in the risk-free asset and the ith stock, respectively. And so they're going to evolve according to the following. So the wealth in the risk-free assets will grow at the rate R. And then there are the 2 terms for buying and selling the stock, right? But for every, let's say for every dollar that we want to buy the stock, we're going to be paying 1 plus lambda dollars from our risk-free asset, basically cash position, and vice versa. Anytime we want to sell $1 worth of stock, we would only get 1 minus lambda multiplier of that, so 1 minus lambda dollars. Deposited back into our risk-free asset accounts. So the trading is going to be is going to be modeled via these process Li and Mi. Right continues with left limits, starting from 0, that are going to represent the cumulative amount of wealth of buying and selling the stock I, respectively. And for simplicity, as very typical, we'll assume that the proportional transaction costs for every stock and for both buying and selling are equal and equal to lambda. So let me define the solvency region K. So this is going to be the region where if you were forced to liquidate your position immediately, then you would not be bankrupt. And we'll use the standard power utility, powers between 0 and 1, because otherwise numerically that's quite difficult to solve. And then we'll define the value function V to be the supremum over all admissible strategies in the classical sense of the expectation of the utility of the terminal wealth, which is liquidated at the terminal time capital T, and so we'll have to bear the transaction costs. Everything's going to work fine though, because things are going to be at least non-negative, and so everything will be well defined. And again, very classically, it's well known that one can reduce variables, reduce the dimensions. And so if we do that, if we make basically this change of variables from the original value function V to the reduced value function U, then this reduced value function will satisfy this HGB equation, where the operators L, BI, and SI are again related to the classical operators. So the BI and the SI are going to be first order operators for buying and selling stock I, respectively. These are going to be nice operators. L is going to be a little bit more problematic. This is going to be the second order diffusion operator that's come from the generator operator, basically. So that's all nice and classical, and so now I think the idea is clear. So we try to discretize the differential operators and see what we can do. And as I hinted, the first order operators do not create any problem. You can basically discretize it, I'll say, almost any way you want. Classically, it'll be first order downwind finite difference. So that's all nice. Ideally, you would apply the same thing to the operator L, but that's where a lot of problems will come. And specifically, the first order part of L is again standard. There's no issue. There is really only an issue with the second order part of the operator. That's where the tricky part is. And specifically, it's the correlation. Somehow, not surprisingly, if you have non-zero correlation, then if you're just going to naively discretize it, then you may, and very likely you will, lose the monotonicity of the scheme, and then basically all this proof that I presented so far is going to be ruined because you're not going to have convergence. Luckily, there is a way out, right? So you can one way to maybe to try and address it is to, of course, to try and remove the correlation, right? So you can go and diagonalize the operator via change of variables, right? So that works nicely. That's again very classical. But then the resulting problem is that you'll be stepping outside of the grid points, right? So that's the price that you have to pay. Now you're going to be somehow outside of the grid points. And if you're not careful and you will continue with the naive discretization, you will have in fact, an operator that may not be even consistent, right? So if you'll discretize it in a naive way, then again, your operator will not be nice and will not be consistent, and you will again lose the convergence that we're working so hard to establish. So here is another solution, and that is to somehow to try and discretize things carefully and smartly, and that is to use a larger stencil. So you will use somehow non-traditional, you'll use points further away from the point that you're discretizing, specifically of the length of order square root of delta z. And again, and then you can use a classical bilinear interpolation weights to now get only a second order accurate scheme, but the benefit of all this hard work is that your scheme will remain monotone, which will ultimately and you can ultimately show that it is ultimately also degenerate elliptic. And this was the idea of this paper by Chen and Wang. And so that's one technical difficulty that needs to be overcome, and that is basically that's created in fact only if the correlation is non-zero. If the correlation is zero, there's no problem, and you can just keep using the classical discretization. In that case, and only in that case, you can show that the scheme will remain monotone. So you will, if correlation is zero, you will not lose monotonicity if you do the classical discretization. And so that's kind of another hint why this correlation creates so much issues, because basically it effectively changes the property of the classical property of the scheme, and again hints as to why it's so difficult or maybe impossible, in fact, to prove smoothness. But so once we show that, now we basically we're back in the game, and we can show exactly the properties that we need. So specifically, now that we have our finite difference scheme, which I didn't really specify, but it is in the paper, that right, so we take now the minimum of the operators L, right, and the BI and the SI operators. So now it will have all the needed property, right? The proper, degenerate parabolic, Lipschitz continuous, consistent, all the needed properties that we need for basically both the convergences. All right. So that's basically kind of the technical part. So technically it works, right? There are a lot of difficulties again, and unfortunately, it's the proof and the construction for higher dimensions needs to be quite manual for this to work. But again, so that's why the illustration is really in 2 dimensions. But in 2 dimensions, it converges, it works very nicely. So here's more or less a classical list of parameters. So this is for the case of the uncorrelated stocks. Right, so yeah, so if you now solve it, and this is the node trade region with the different levels of transaction costs. These are the neural network approximations. So they work quite nicely. Yes, things are not perfect. More interestingly, here is what happens if you do have correlation. So this is the same correlation that was used in quite a few papers, I think starting from Mortharamon and Kumar, where basically they fix the correlation times the sigmas, right, and then adjust the correlation matrix, right, and then so we do have these nice properties. Again, if you are to zoom in, yes, you will see that this is not very perfect and still a numerical scheme, but at least fundamentally all the desired properties are there. And so when, for example, as as correlation becomes negative, right, then the main diagonal will elongate, right, for the non-trade region, because right, each asset can also be partially used as hedge. Right, so basically the key is that yes, it does work very nicely in 2 dimensions. Again, the big issue in multiple dimensions is that one has to be very, very, very careful with the scheme and basically reconstruct the correct scheme by hand. And that becomes quite cumbersome in very high dimension because of these properties that you lose the monotone and the general ellipticity of the scheme if you're not careful and just try to approximate it using the kind of the standard classical naive finite difference. Then it will fail to converge. So I'll conclude now, and I'll say that so we presented a way to numerically solve a PDE by basically having this intermediate step and incorporating adding a convergence to a finite difference scheme, right, and then showing and then using the fact that we know that the finite difference scheme converges to the true solution. And so we were able to do that and then to show that our neural network also converge to the true solution. And we illustrated for the problem of optimal investment with transaction costs. Although again, our problem is not really limited to that. It can be more general, but that was always the motivation. So I'll stop here. Thank you.
Thank you. Thank you for this talk. I believe there was one person raised hand, but I don't. About 2 minutes ago, I saw someone is raising hand and it went away. If you have a question, please raise your hand again. I don't know who that was. I don't have time to read the name. Nobody?
I have a question.
Go ahead.
So are you able to get any form of rate out through this argument, given that you're going through the finite difference scheme? It seems that the rates you get would be quite poor in terms of dimension.
Ultimately, yes, I think the big issue is again kind of the fact that you have to hand adjust the scheme, right, and then because again I mean, unless your correlation is 0, which in this case basically everything is nice in any case, right, and then you don't have to work so hard, right, then you need to do all these manipulations to work on the scheme, and I think that's the hard thing. So if you're going to give me something that's like in really truly high dimension, that's going to be a big issue. So that at least I'm not aware of like a nice automatic algorithmic way to do it.
Thanks.
Can you explain that part? Essentially, you need to choose your grid points appropriately, right? That's what you're saying.
Yeah, I mean, well, so I mean, the appropriately is, I mean, that's kind of, I think of it as a kind of part of the finite differences, right? So the finite difference will chooses the, or I guess, okay, let me maybe clarify this, right? The grid is fixed, right? The grid is fixed, and that's kind of the standard finite difference grid, right? The issue is that if you're not careful, right, then if you try to use that grid, right, and discretize it in a simple way, then it doesn't work, right, because the operator is bad. So if you then change variables, you're going to be stepping outside that grid, right? Which is basically also not good, right? So if you just want to try and discretize it once you're outside, you don't have to change the grid, right? You can just interpolate. But if you do that, you'll still end up with a bad operator. So you need to do this large stencil grid, and you lose the nice convergence. You get the square root convergence. That's the part that basically that you have to do. You're not actually going to change the grid points, but you will change the values that you're going to use, and they're going to be further away. They're going to be square root away from the center, as opposed to kind of the classically, which is just delta x or delta t away, right? So 1 or 2 points away.
I see. Okay. Rene has a question. Thank you.
Can you hear me?
Yep.
So why do you choose to approximate the finite difference solution by a neural network? Why not, modifying the value function so it would be smooth? You still control the error and then approach the modified version by a neural network. How would that compare?
Right. Yeah, we tried that. The problem is that if you do not you really don't have smoothness, right? It's really only a viscosity solution, right? Then the modification is going to be quite badly behaved ultimately, right? It will converge to something with non-smooth derivatives, right? And so that all still fails. That's really the issue, right? So ultimately, we are kind of swiping the non-smoothness under the rug by going exactly through this finite difference, right? And then trying to approximate finite difference instead of approximating the original function, which turns out that it is easier. But yeah, that was also exactly the points that we were struggling, and we were really trying to do it because that's kind of the intuitive way. We couldn't make it work.
Thank you.
Thanks, Rene.
I have one question again about this. I mean, I have the impression that if you have smoothness a priori, right, you should be able to say that your L2 error is not from an L2 error with respect to Lebesgue measure. And then if you have some regularity estimate, you should be able to say that it is a L infinity error, which is usually independent on the size of the grid. But
Yeah.
that if you put a little bit of regularity, you might be able to say that your C is independent of the size of the grid, which will be interesting by itself, I think.
Yeah, I mean, if you have regularity, then everything becomes a lot simpler. Basically, a lot of other methods converge and things work really nicely. It's the key was really if you don't have regularity. That was the key for us. I have quite a few proofs if things are smooth. If you know a priori that things are smooth, that they're that things work out really nicely. That's it's really the this method really is to really overcome the non-smoothness, that if you don't know smoothness a priori.
Okay. Thank you. Thank you very much.